Thanks to those. Thank you for those who have joined. People are still joining. We'll give people 30 to 60 additional seconds before we begin, but then we will get immediately to today's webinar. Welcome to today's CMI webinar, the first webinar of 2025. I'm Rod Eggert, CMI Deputy Director and also a faculty member at Colorado School of Mines. Today, we're especially excited about the webinar for two reasons. One, it's the 100th CMI webinar over our 12 years of operation. And second, the topic today is especially interesting, redox flow batteries. We're delighted to welcome Clifford Krowne from Ashlawn Energy to talk to us about science, engineering, and manufacturing aspects of redox flow batteries. Next slide, please. Let's start with just several administrative details. We're always thinking to the future. If you have a suggestion for a future webinar, please include it in the exit survey that you will receive at the end of this webinar, or you can always email it to cmi@mines.edu. This is a public webinar. A recording will be available next week at aimslab.gov/CMI on our YouTube channel. And finally, and very important for today's webinar, if you have questions, please type them into the Q&A box at any time during the presentation, and we will be monitoring that box. Next slide, please. A bit more about Clifford Krowne. He is a former research scientist at the Naval Research Lab, now at Ashlawn Energy. He's had significant industry experience with interest and background and experience in theoretical and applied physics and other areas. He has more than 200 peer-reviewed science publications, and his most notable instructor was the Nobel Prize laureate in physics, Julian Schwinger. With that, let me ask Cliff to advance to the next slide and give him the floor. Cliff.
Thank you very much. So you've already seen the title. I'm an emeritus from NREL, and I'm the Chief Scientific Officer of Ashlawn Energy. I'm not going to read through this whole abstract, but just to tell you that the flow batteries are a very complicated beast, if you can say that. They involve partial differential equations to solve the problems, concentrations of electrolytes, current densities, fluid motion, to name a few key things that are going on. The battery structure includes bipolar plates, conductive plates going in and out, electrode regions, that's where the chemical action happens, and there's a membrane separator. There's been extensive theoretical and experimental studies for redox flow batteries. That's all I'll say about that. Well, here's a diagram of battery that we are building, actually, and we've studied theoretically. So you see there's a, on the left-hand side, there's the negative electrolytes with ions, vanadium +2 and vanadium +3. And on the right-hand side, the positive electrode is vanadium +4 and +5. And you can see the general battery structure has a negative current collector, a bipolar plate, that's in white, the negative electrode, the membrane, the positive electrode, and then the same type of bipolar plate and current collector plate. And you have to flow fluid in and out of these electrodes separately with separate pumps. So there's a number of equations that determine how this battery works. And for the fluid flow, what you have is key equations. The key equation really is the Navier-Stokes equation, well known in fluid mechanics. This equation here says that the density times the rate of change of the velocity is equal to the force times the density minus a gradient of the pressure term, and then a term involving the squared operator, del operator onto the velocity times mu, which is a viscosity. The total derivative operator here is just defined in the next line. It's the partial with respect to time, that partial derivative, plus the velocity times the gradient operator, spatial operator. It turns out for incompressible fluids done in low turbulence parts of the battery stack that this divergence of the velocity is generally roughly 0. More details are found in the bottom of this view graph, and that's in the Journal of Electrochemical Society, published last year. The next view graph, hopefully it'll come up.
Cliff, I think you need to control my screen again for some reason.
Yeah, I'm trying to do it. It doesn't seem to be advancing it. There it goes. It went 2 at once. Okay, let me go back. There we go. The next screen describes the fluid physics for the redox flow battery again, but it talks about the pressure change between 2 different heights. And of course, there's a vertical aspect to the battery stack as well as a horizontal aspect. So this is a very important equation. The first equation is Bernoulli's equation regarding pressure, velocity, and gravity, potential energy. And that equation says that the pressure at any slice along, say, a pipe feeding fluid into and out of the battery, plus the kinetic energy, that's the 1/2 rho times velocity squared term, plus the potential energy, rho times the gravitational constant times the vertical height y is a constant. A very famous formula that comes out of this related to this is Bernoulli's equation regarding cross-sectional flow areas. That says that the velocity of one slice times that area of that slice is equal to the area times another slice times the velocity in that second slice. And you can see that in the diagram. The left-hand part shows you A1, pressure 1, velocity 1, and the right-hand side shows the area for the slice 2, velocity 2, and location x2, and height Y equal H2. This information is at the found in detail in the publication, bottom of the screen. Okay, here's the next view graph. Let's see if it does that. For the next view graph.
Cliff, I think you need to control my screen again.
Yeah, I'm trying to do it. It's
Rod, I think it would be better if Cliff just told you next slide. Then there won't be the delay.
yeah. Can you do that, Rod? Just do the next slide.
Okay. How's that?
That's great. Thank you.
Okay. I will advance
Okay.
slides.
Good. So there's a lot to fluid physics for the redox flow battery. And one of the most famous laws that's used is called Darcy's law for velocity and pressure. And you can see that at the left-hand side of the view graph, that the velocity, there's a vector, is equal to kappa over mu. Kappa is the permeability, and mu is the viscosity, and it's times the gradient of the pressure. And you can see the little cartoon diagram has a pressure on top and pressure on bottom, and shows the green arrow with the Q is the flow. And in this Darcy's law can be seen on the right-hand side. It says that the flow, the left-hand side is the continuum equation. The right-hand side shows the flow written in terms of the pressure difference between the top and bottom divided by the distance L. And again, times kappa over mu times the cross-sectional dimension. That's A sub CS. And the pressure difference is between the top and bottom. And the information on this can be found in the publication at the bottom of the screen. Next slide, please. Thank you. So there's a number of important measures for any redox flow battery, and you can see that here. The most important ones are called the state of charge, and they really measure the percentage of the ions that lead to a operation of the battery divided by the total charge in the negative electrode. And you can see that left-hand side equation said the state of charge, COC superscript minus is C charge of the plus 2 ions over the total in the negative side electrode, which is C plus 2 and C plus 3. The positive electrode, as you'd expect, would be something similar, but the key ions are the plus 5 and plus 4 ions, so C plus 5 or C plus 4 plus C plus 5. So that's the state of charge, and also this key various efficiencies that are evaluated for the batteries. And these are the coulombic efficiency, the energy efficiency, and the voltage efficiency, and I'll detail those right now. They're all given by integrals. The first one is the Coulombic efficiency, is the integrated discharge current divided by the integrated charging current. That sort of makes sense. The energy efficiency is just to the voltage E, so discharge, times the current discharge, So that's basically voltage times current over the, and that's over the discharge cycle, and divided by the same product due to the charging, voltage and charging, and current and charging over the integrated charging time. And the last one roughly is equal to the product of the, well, it's the energy efficiency divided by the Coulomb efficiency, but that's only an approximation. But I just showed it to you because that's a simple formula. Okay, but what happens in a real battery that's got pumps? We talked about that earlier. You have pumps and pipes. So to handle that, we have to go to the next view graph, please. So if you take a look at this view graph, you'll see that the energy efficiency is a little bit nuanced. So I've called it eta sub E, pumps plus pipes. So get this, do it correctly. I have to take the integral in the discharge time, E discharge times I discharge minus the power consumed in the negative electrode pumps and pipes and the positive electrode pumps and pipes. You subtract that because that's not useful power. So that integral gives you what you're getting out usefully. And then the power consumed is not just the power of charging, which is E charge times I charge in the bottom, but the power expended in the pumps, again, negative electrode side pumps and positive electrode side pumps, and the integrated of the charging time. So you can see that formula. So that's the real, more accurate assessment of the energy efficiency. Now, the second formula is a very, very interesting formula. It's the energy density for evaluating battery capacity. And it's a very important quantity and often used for evaluating batteries of many different types, not just vanadium batteries, but all types of redox flow batteries. And it's made a product of three factors. The first one is the total ion concentration found in either negative or positive electrode regions. Then it's times the Faraday constant, and then times the discharge voltage. That's the terminal voltage across the stack. And that makes sense because what you deliver in useful power is due to the discharging of the battery. Information on this can be found at the publication at the bottom of the view graph. Next view graph, please. Now, there's quite a few key governing equations for simulating the battery and understanding it. And I've shown those on a few slides. So this slide shows the ion flux. That's N sub I for the ice species of the electrolyte ion. And it's got three contributions. One is due to the diffusion constant times the gradient of concentration. That makes sense. Next one's due to electric fields. So that one's got a diffusion concentration times the gradient of the potential, local potential. And the third contribution is that's what you would expect. You've got flow going on, so it's the velocity of flow times the concentration of the ice species. The next key equation gives you the current density, and that you can see is just the product of the ionic charge on the ion times the Faraday constant times the flow given above. Charge neutrality has to hold. We don't build up excess charge in a battery. So that means that the charge on these ions, Z sub I times the concentration C sub I, that product summed up of all the ion species would give you 0. And finally, the time rate change of concentration of the ions is an important quantity to think about. That's the rate of change of C sub I with respect to time. That's that flux flow is given by the negative divergence of the flux above N sub I plus the various sources or sinks. And that is a very interesting second term, but I won't go into detail. So you can find that in the publication at the bottom of this view graph. Next view graph, please. Well, here's a pictorial diagram of what's going on. This was taken from the publication at the bottom of the view graph. And you can basically see here, I've shown you the negative current collector The fibers in the negative force electrode in the what's called the proton transport membrane. You can have membranes that operate with either positive ion or negative ions, but the vanadium battery that we use with the membrane uses a proton transport. And the equations on the right-hand side just tell you about some of the current terms. The current on the negative side in the fibers is given by the conductivity times the gradient of the potential, which is essentially electric field. And that conductivity in the fiber is roughly constant. But for the electrolyte current, that's given by the conductivity electrolyte times its gradient in the electrolyte. And the conductivity is a complicated product of the charges and the concentrations times the diffusion constant. I won't derive this, but the derivation is given in the publication below. I do mention a few ions, charges, the V plus 2 ion, the V plus 2 is 2, V plus 3 is 3, hydrogen is plus 1, hydrogen HSO4, negative ion is negative 1. Anyway, that gives you a little pictorial diagram with some of the key formulas that are going on. Okay, let's do the next view graph, please. Now, this is a little bit of a magnified blow-up of the previous view graph. And we zoom in on the interface between the electrolyte, which is shown in yellow here, and the green, which is the fiber. And if you take that region below to farther, on the right-hand side, you can see that you've got a current in the fiber flowing and a current in the electrolyte flowing. And the normal currents, where you can't build up charge, or if you don't build up charge, you have to have a continuity of those two currents. So the current in the fiber should equal the current in the electrolyte. And the normal components are shown in the equation below that little box diagram. And the equations that give the electrolyte fiber currents are shown below that. The conductivities in the electrolyte or the fiber should be greater than 0. And you would expect the potential, there'd be a potential difference between the fiber and electrolyte. So that would be, in the last equation, that would be not equal to 0. Okay, next view graph, please. So, well, we did the battery stack, but you're wondering, you have to have tanks that store the electrolyte because it's a redox flow battery. So the change in the inlet concentration going into the battery with respect to time in the first equation, it's got to be equal to flow rate Q over the volume of the tank times the difference of the outlet and the inlet concentrations. And the tank concentrations you're going to wonder about, and that can change too. And that has a similar equation, the second equation below. And Q is the flow rate into the battery. It's given in moles per unit volume per second. And more details on this are given in the publication at the bottom of the view graph. Okay, let's go to the next view graph. Now, you work with all these equations, and I won't do it here, but it's in that publication at the bottom of the view graph. You can get some information out, very interesting information. The left-hand column has types of loss mechanisms. The right-hand side talks about the loss, of course, losses and watts. So negative and positive electrodes, there's activation energy losses, chemical reaction losses of the negative and positive electrodes. So the first 3 rows give those numbers. It's 0.02, 0.06 to 1.54 watts. The negative and positive electrodes, you can see, are vastly different. The negative electrode looks like it's an average of about 4 watts, whereas the positive electrode must be much more conductive and it's much less. Looks like roughly about 0.7 watt loss. Now, that's the chemical reaction loss. The negative and positive electrodes have ohmic losses, and those are tiny. It looks like that would be roughly 1 watt. And the similar to the positive electrode loss, a little bit different, but roughly a watt again. And then the current collectors, the ohmic loss there is very tiny. These are meant to be highly conductive to take the current in and out of the battery. So you certainly don't want them to have a lot of ohmic loss. So that looks like it's 100 times smaller than the previous ohmic losses. And then there's cooling from the injector electrolyte. It comes into the battery. And so its loss is a negative number, negative about 21 in watts. Okay, let's go to the next view graph. So it's got the same loss mechanisms in the left-hand side column, but the right-hand side column talks about the temperature rise. So that's very important because you don't want the battery to get too hot. This has been a problem with the other type of solid-state batteries, with lithium batteries in particular, from cell phones to laptops to power units in various vehicles and structures. So temperature rise is a very important quantity. You can see that it's given in Kelvin per hour, how much this rise would be. So so for the activation loss, it's between 1 and 47 Kelvin. The chemical reaction losses in the negative electrode is, you can see it's roughly, it looks like 100 roughly. And the positive electrode is much lower. It looks like it's roughly about average 25. The ohmic losses, negative and positive electrodes, are significant. You can see that. Looks like it's at least 20 or 30 in the average. And the positive electrode looks like something similar, maybe 30 average. The collector, current collector losses, ohmic losses, are very tiny, and they're just a fraction of a Kelvin per hour. Whereas the cooling from injector electrolyte is enormous. It's like 450 degrees Kelvin per hour. So the cooling is enormous. So that's good to know, because if you don't cool it, you're going to have a thermal runaway, and that would destroy the battery stack. Okay, let's go to the next view graph. We're going to take a walk into quantum mechanics, because there are quantum mechanical aspects to what goes on in the battery, because you're having little local interactions between chemical constituents. So this is very important. It's a key equation. If you look at this, it's a diagram of the free energy for the oxidant and reductant configurations, and the key quantum mechanical spatial parameter Q, its coordinate. And the diagram has a vertical axis, the standard Gibbs free energy, and versus Q, the momentum coordinate. And you can see, you can go from the yellow curve, which has the oxidant, and that's to the reactant, that's the green curve. And where they intersect is where you can have a change of behavior and basically a electron exchange. So you can see you go from a minima of the Q naught, the local minimum of the oxidant, and there's the minima of the local Q sub r, local minima there on the right-hand side. And so you can see that there is a change in the Gibbs free energy going from left-hand side to right-hand side, going from an oxidant to a reductant. So this type of diagram is a key diagram describing the phenomenon. Next view graph, more on quantum mechanics. So this is a very interesting view graph because it talks about one of the key equations used to simplify theoretical modeling. It's the Butler-Vollmer equation. That can be related to quantum mechanical aspects of the chemical reactions. The first equation talks about the chemical reaction current, which is the electrolyte current, and it's equal to an exchange coefficient times the difference between two exponentials. And I'll tell you what's in it. Each exponential has the gas constant times temperature in the denominator into a coefficient, N-noic coefficient times N sub K. That's the electron exchange in the chemical reaction times the Faraday constant. And eta sub K here is the overpotential. It's the potential that happens in a battery when it's not in equilibrium. When the battery is in equilibrium, that would be zero because there's going to be obviously no current flowing. And that there's two exponentials. It's the difference between those two. Between the second term is a negative of that exponent, and it's times alpha sub t, the cathodic coefficient. Now, this has a quantum mechanical version using the Gibbs free energy, and it's the second equation. You can just replace the exponential constants by the change in the Gibbs free energy in the anoic side with respect to energy times the overpotential divided by gas constant times temperature minus the cathodic term. And this information is available in two papers at the bottom of the screen. Okay, let's go to the next view graph. All right, so that's a little bit of walkthrough vanadium redox batteries, and in particular, well, in general, redox flow batteries. So this are publications and activities. Some of the publications that I referred to at the bottom of the screen of each view graph were given here. And our activities lately are given from 13 to 18. We've had an underwriter laboratory certify our medium-sized battery stack and system. That happened in November of this year, last year, November 2024. We're going to be installing redox batteries in various multifamily apartment buildings. We are doing membrane research with Rensselaer Polytech Institute in Troy, New York. That's beginning in December. Began already in December 2024. We began sensor research with leading universities beginning in past December. And Ashlawn batteries are being deployed to long-duration energy storage facilities in New York City. And we expect future installation of the redox batteries in various New York hospitals with agreements being made in December and January last year and this year. Next view graph, please. Now, this figure is taken out of the publication at the bottom of the screen, and it basically shows two very interesting diagrams. The one on the photo on the left shows the battery stack components being put in with guide rods vertically, and you can see the stack, which is turned on its side to stand vertically, and it's held together by many bolts, and you can see that. And this is from earlier work that we've done, and I want to show you this stack in the next view graph when it's being tested. Next, yeah, that's it. So this view graph is very interesting because it shows the stack in operation. It has 9 cells, and it shows the electrolyte tanks on the left, the stack on the right, flow temperature sensors indicated here. It shows where the pumps are, lower part of the diagram there in black and blue, and variable frequency drives are shown on the lower left-hand side of the photo. Okay, next view graph, please. This just shows our Chief Technologist Maurice Daniel sitting next to some storage containers containing the electrolytes. Next view graph, please. This is a very interesting photo because it shows that during operation, you can identify the negative and positive electrolytes going to the respective electrodes, depending on the valence states. In the photo, the upper tube is carrying fully charged positive electrolyte, V+5, which has a yellowish orange color, while the lower tube carrying the fully charged negative electrolyte, V+2, is a dark purplish color. Next view graph, please. There's a very, very interesting diagram. It turns out that there's many different possible what's called half couples for making either the negative or positive electrodes, but you have to choose them intelligently. So you can see the vanadium redox flow battery has the V3+/V2+ in the sort of lavender region, left side of it almost. And in the middle of that region is the VO2+, V3+, and then in the farther over is the VO2+, VO2+. That really can be shown to be the +4 and +5 ion couple. So you notice they're in the lavender regions, and that's very important to notice because if you get in either the left-hand region, you'll get hydrogen evolution, hydrogen gas evolution, and if you're in the right-hand side, you get oxygen evolution, gas, and you don't want that either. So there's a window of useful opportunity in which to operate these half-cell couple for the stack. And of course, you take two half cells together, you get the total voltage, which in a vanadium battery would be about 1.26. This is discussed farther in the right-hand reference. The next view graph, please. So this view graph shows something we've done very recently. This is our most recent pre-manufactured three-cell stack vanadium redox battery, and you can see the battery stack on the right-hand side of the diagram. The tanks more toward the middle, and the pumps on the table more toward the middle. And the left-hand side of the diagram is the control unit with the monitor and the brake controls for the pumps. And this was put together in order to certify the battery and have an underwriter laboratory give us a certification. This happened in the end of around November 2024. Okay, and the final slide for you to look at is here. This one shows a little test 4 by 4 by 4 square redox flow battery stack from Charles Tanzola of TDM Fuel Cell. And this is very interesting because with this small miniature battery stack, we can test different membranes or different ideas out without having to go to enormous expense to make a full up battery, the ones you just saw, which very large cross section. So large cross section batteries are thinking is to have them run between 10 kilowatts and 50, whereas this is very small amount of watts. Okay, and I should say that at the bottom of this description, it's the collaborators on this include the professor chosen by Department of Chemistry and Chemical Biology, RPI in Troy, New York. Okay, I think the next slide has my contact information, and contact and publication information as to locations. We're both Ashlawn's located with a main laboratory in Binghamton, New York, and a facility in Springfield, Virginia, and we also have a local laboratory we can build and test small batteries, which we utilize. Okay, next slide, which is the question and answer portion.
All right. Well, Cliff, thank you very much for this very interesting overview of vanadium redox batteries. We now come to questions and discussion. Please use the Q&A box to type in your questions or comments, and I will monitor and manage this portion of the webinar. I might begin by asking you, Cliff, to tell us a little more about Ashlawn Energy. You touched on what Ashlawn is doing briefly at the end of that list of publications, and with the photos and descriptions of various things in the latter part of the presentation. But can you tell us a little more about Ashlawn Energy and kind of next steps in your business plan as you commercialize and deploy these batteries?
Well, that's a very interesting question. We're going through several stages of manufacturing and engineering. So it's first the engineering of appropriate end plates to contain the battery, and then constructing the battery in a few cell unit structures. And when that's verified to work, we will then move on to a cell that has, instead of maybe 5 volts for the terminal voltage, we will move up to like 40 volts. So that will move 70 volts, actually. 70 volts. To get 70 volts, you would have like 40 cells put together, not just 3. So that would take us from 5 volts to 70 volts. So that's where we're going. And that would really get us into the range of being able to make 10 kilowatt batteries to 50 kilowatts. Furthermore, we can combine these. We can take these basic 10 to 50 kilowatt unit stacks and put them together and obtain more current capability or more voltage capability, and thereby get more power or voltage. So that's where we're going with this.
Very good. Thank you. We have a question from Jayhone Lee, who asks, if vanadium flow batteries are implemented on a large scale, do you expect there will be a shortage of vanadium metal? What are your thoughts on the availability of vanadium associated?
That's an interesting question. Yes, that's a very interesting question. Vanadium, there's several good sources. There are sources in the United States, many more sources of vanadium in Australia. And I actually just was involved in reviewing a paper for all of Australia in terms of vanadium availability and redox flow batteries in the continent of Australia. So I can tell you that vanadium is a very pleasant element to work with because it is available in the free world, unlike, say, lithium, which is mainly mined in China, which creates a real problem for the free world. Furthermore, there's a very interesting facet to vanadium. It turns out that from petroleum processing, you can get vanadium from that processing. Finally, it turns out that vanadium from electrolytes can be recycled. So once the lifetime of a battery ends, you can recover all the vanadium, just nearly all of it. So it's very friendly for the environment. And I should just mention something else very interesting about vanadium. batteries. They do not have the fire hazard problem of lithium batteries, which is both being able to burst in flames and or explode. This is one reason why vanadium-based batteries are so important, and why we also view one of the important markets for us to be in modest size energy. We can basically provide modest size energy in both cities, rural areas, and so the batteries could be really deployed any place in the continental US or outside in Europe, Africa, South America, Asia, India.
Well, Cliff, thank you very much. We do have a minute or so for one other question, if there is one. While people are thinking about potential last question, let me just thank everyone for attending. And Cliff, let me thank you very much for presenting this insight on an emerging and likely very important battery technology. We at the Critical Materials Innovation Hub thank you very much for your meeting with us and talking with us today. As the slide says, the recording will be available next week on the CMI YouTube channel. A bit of advertising. Our next webinar will be about a month from now, actually 2 months from now, on March 25th, when Sam Palumbo will present DISA Technologies, an introduction to high-pressure slurry ablation technology. And details of this will be available in the Critical Times, as well as on the CMI website and on the Ames National Lab social media. Finally, if any of you do have suggestions for a future webinar topic or presenter, please share it on the exit survey or email us at cmi@mines.edu. So again, thanks everyone for attending, and thank you very much, Cliff, for this fascinating presentation.